They also, the beat up soil rapidly because of the concentration of therapies in they're also
Okay, I guess we should get started. Are there any questions about the homework at this point, or any issues from the last class? Okay, then I guess we can move on to our next topic. So what we're going to be looking at today is the issue of mixing time sounds. And this relates to the issue of mixing times we talked about a few lectures back relatively briefly. Does anyone remember what a mixing time is in a Markov model?
time it takes to get to steady state.
Yes, it's a measure of how long it takes before the Markov model is close to its steady state. And we had briefly seen some ways of quantifying that. And let me just restate those for the moment. So we had looked at a measure of distance between the steady state and the current state of a Markov model, known as the variation distance. And we had seen that there are a few different ways of defining that, but the one we were going to use is denoted by delta sub q of t, and this refers to the maximum over subsets of our state set q of probability of the current state at time t, or step t being in S, given that the initial state was our state q here, minus the sum over qi in S of pi I. And what we're trying to ask about here is, I guess I should probably put an absolute value here. So what we're trying to ask here is, how far is the Markov model from its stationary distribution? So we have the stationary probabilities pi, we have the current probabilities after t steps, and then we denote the maximum difference over subsets as the variation distance. And what we're interested in is how long it takes for the variation distance to get small. And as we had seen, a formal way of denoting that is what we'll call tau sub q of epsilon, which is the minimum over steps t of such that delta sub q of t prime is less than or equal to epsilon for all t prime greater than or equal to t. So how many steps t do you need to run the model before you are guaranteed that the variation distance is smaller than epsilon for all times going forward? And that's just a formal way of stating the mixing time of a Markov model. And generally what we're going to want to do is show that a Markov model, or design a Markov model, so that it has a small mixing time. So as we saw in the previous few classes, very often what we're interested in doing with a Markov model is trying to estimate the stationary probabilities. So we really want to know, when we run the model long enough, that the current probabilities, how often it's spent in each state, are a good estimate of the stationary probabilities. So does that make sense to everyone? Okay, so our goal today will be to see some ways we can prove bounds on the mixing time. Usually it's not going to be trivial to prove an exact mixing time. As we had seen, there are ways of getting at that by doing an eigen decomposition of the transition matrix of the Markov model, but that's usually going to be a pretty complicated thing, and the interesting Markov models are usually large enough you don't actually want to deal with this. But there are some techniques we can use to try to show that the mixing time is no more than a certain bound. And very often what we're specifically interested in for large Markov models is showing that they are what is called rapidly mixing. And rapidly mixing is a concept related to the concept of tractability in discrete algorithms. So we say a Markov model is rapidly mixing if its mixing time is polynomial in the number, or basically in the parameters of the Markov model. So typically polynomial in the number of states, or the number of input variables to the problem, or the size of the problem you're modeling. We'll see some examples of that. So what I want to do today is go through 2, and if we have time for it, 3 different techniques we can use to prove that mixing times are bounded for particular Markov models. I'm going to start by jumping right into one of these called the canonical path method. Now, before I get to exactly what this method is, I should say that this method and the other ones we'll see do make certain assumptions on the model we're looking at. And the first step in these methods is really to verify that the assumptions are valid. And usually they're not too hard to verify. So one of them is that these don't work unless we have an ergodic Markov model. So does anyone remember what ergodic means? It means that it's possible to get from any state to any other state in some finite number of steps. So it's usually not meaningful to talk about stationary distributions if your Markov model isn't ergodic. We will want to insist that PII greater than or equal to 1/2 for any state I. So PII is the self-transition probability. Basically, we're asserting that when we do these proofs, we want it to be true that every state has at least a 1/2 self-transition probability. And that's a pretty trivial thing to guarantee because it's very easy to take any Markov model and turn it into one that has this property true. Basically, oh, is there a question?
You were going on to explain it, sorry.
Yeah, and pretty much what we would need to do is if we have a Markov model where that's not satisfied, so let's say we've got a model that looks like this, we've got maybe one state where it is satisfied, but one state where it isn't, we're just assuming we have a 0 self-transition probability in this state, then we can turn this into a Markov model that satisfies this condition by just dividing all of the probabilities by 1/2 and then adding 1/2 to each self-transition probability. So this one, we divide by 1/2, we get 1/4. We add 1/2 to that, we get 3/4. This one, we divide by 1/2, we get 1/4. This one, we divide by 1/2, we get 1/2. And then the initial self-transition probability here was 0. We divide that by 1/2 and add 1/2, we get 1/2. So this is giving us a model that is not equivalent to our original model, but basically is slowed down by a factor of 2. So it's equivalent to saying on each step, flip a coin and with probability 1/2. So if you get heads, just stay where you are. Otherwise, do what this Markov model says to do. So it's a pretty easy change to make. And the last condition we need to assume is that our model exhibits detailed balance. So does anyone remember what detailed balance is?
Is that when you go in one direction, it takes the same number of steps to go in the opposite direction?
Well, not quite the same number of steps. You would test for this by showing that for any cycle, the product of probabilities of going one way around the cycle is the same as the product of probabilities going the other way. So that we call it the Kolmogorov criterion. But the formal statement of this is that for any states I and j that are neighbors in the graph, we have pi I, pij equals pij, pji. Now, very often we're going to be working with Metropolis or Gibbs samplers when we're interested in these techniques, and those we already know satisfy this condition. In other cases, a model that we're given, so one that comes up naturally as a model of a physical problem, may or may not satisfy this, so that's something where you'll want to prove that it's true, and if it isn't true, you might need to redesign your model to get something where these techniques apply. But usually that's not too hard to guarantee, and most often where we're using these techniques, it's because we want to sample a stationary distribution, and usually the models we'll be using for that will be Metropolis or Gibbs samplers. We know this is true. And so any questions about any of that? Okay, well, let's say then that these properties are satisfied. Then the canonical path method gives us a way of showing that the mixing time is no more than a certain bound for that model. And to give some intuition behind the canonical path method, we can imagine that we've got some Markov model graph. So let's say this is a graph that's describing transitions among states in the model. This can't can't exhibit detailed balance unless the edges are all bidirectional, so I'm only drawing them one way, but you can assume that they're all bidirectional. So what the canonical path method says is that essentially, if you can pick a way of getting from any one point to any other, and you can do this in a way that no individual edge in the graph gets too much use on all of these paths you're picking, then you can show that the Markov model doesn't have a long mixing time. So in other words, what we have to do is, for any state I, let's say Qi, and any state j, Qj, we pick some path between those two states. So maybe for this I and j, we would say this is the path between them. And maybe if we have a Qk here, we have to pick a path from Qi to Qk. Maybe we'll say it's this. Maybe a path from Qj to Qk. Maybe we'll say it's this. Just for any pair of nodes, we pick a path. And the proof technique can apply for any paths we pick. We get to pick what the paths are, but the quality of the bound it gives is going to depend on the paths. And once we get through how you actually use this, it'll be a bit clearer what you want to look for in a good path set. But basically what we want to do is pick these paths, and I'll use the notation gamma sub ij to mean the path from Qi to Qj in our path set, and we'll use a capital gamma to mean the full set of these paths instead of all of the Qij's. So any questions about that? Okay, so once we've picked our set of canonical paths, so for any pair of nodes we have a path between them, what we'll be interested in is a quantity called the edge loading of paths in the Markov model graph. And the edge loading is something we'll define as follows. We'll say rho of a particular edge, which we'll define to be, let's say, the edge from Qi to Qj, we call that E. So rho sub E is going to be defined as 1 over ii pij times the sum over gamma ij that are using that edge. So I'm using this notation here, this backwards includes, so sum over all canonical paths that use that particular edge of, let's call it I prime j prime, of I prime, j prime, gamma, the length of gamma, I prime j prime. So in other words, we take a particular edge, we take this 1 over ii pij, which is the same term we have in the detailed balance function. I'll sometimes abbreviate that as capital Q sub e, that's known as the capacity of the edge. So we take 1 over the capacity and then sum over all the canonical paths using the edge, this product of the stationary probabilities at the endpoints times the length of the path. And that we know of as the edge loading of E. And then what we're really interested in is going to be the maximum over all of those edge loadings. Let's call that rho of capital gamma. So rho of capital gamma is just going to be max over all of these edges of the row of that particular edge. So the maximum edge loading over all edges in the graph. And what the canonical path method says is, if we can find a way of designing our canonical paths so that no edge has high loading, then we're going to get a graph that mixes quickly. In particular, the formal statement of that is the following theorem. So given a finite reversible Markov chain, and reversible, I'll just point out, is a synonym for having detailed balance. So if a Markov chain exhibits detailed balance, reversible is just a term to refer to that. With PII greater than or equal to 1/2, and max edge loading rho. Tau sub Qi of epsilon is less than or equal to rho times log of II inverse plus the log of epsilon inverse. So what this is saying, in other words, is that the mixing time of the Markov model is bounded by something proportional to the maximum edge loading, and then we end up with this extra term. So this is basically saying if you start in a rare state, it takes longer to mix, one with low stationary probability, but that's usually something we can more or less ignore. And then, of course, the smaller we want epsilon to be, the closer we're insisting it be to the stationary distribution, the longer it takes to run, and that's going to be proportional to the log of epsilon inverse. So basically the bottom line of this is if we can make rho small or show that rho is small for a canonical path set we pick, then we can show the mixing time is small. So is that statement clear to everyone? Okay, so I'll go through how this would work first with a very simple toy example, and then we can see how it would apply to a more complicated kind of real-world biological type example. And I'll put down the following graph as a toy example. So we'll say we've got state Q1, Q2, Q3, Q4. I'm going to assume that Q2 and Q4 will have self-transition probabilities of 1/2. Q1, Q3 will have self-transition probabilities of 3/4. And then the edges between them are going to look as follows. So Q1 will have probability 1/8 of going to Q2 or Q4, and likewise Q3 will have probabilities 1/8 of going to Q2 or Q4, and we'll assume that the probabilities in the opposite directions are all 1/4. Okay, so what I'm going to want to do then is show a bound on the mixing time of this particular model. Right, so the first thing we want to do is verify that the properties we need apply to this model. So is this an ergodic model? Yeah, so anywhere we start, we can follow the edges around and get wherever we want to go. By design, we have all of the self-transitions, at least 1/2, so we're okay on that point. And we need to verify detailed balance. So does this model exhibit detailed balance? Yeah, so if we apply the Kolmogorov criterion, any path we take, there's one cycle, we're going to have probabilities 1/8, 1/4, 1/8, 1/4, and it'll be the same if you go in the opposite direction. So we have the same product of probabilities, so we're guaranteed that this model exhibits detailed balance. In this case, the model is simple enough that we could actually figure out the stationary probabilities pretty easily just from knowing that it exhibits detailed balance. So one of the reasons we are interested in detailed balance is that if you're guaranteed pi I pij is equal to pi j pji, then that tells you that pi I over pi j is equal to pji over pij. So from a model like this, we could pretty easily figure out, just based on the ratio of the transition probabilities, that Q1 and Q2 need to be in a 2-to-1 ratio for stationary probabilities, Q2 and Q3 in a 1-to-2 ratio, Q3 and Q4 in a 2-to-1 ratio. And the only way we could guarantee that is if pi 1 was 2 over 2 plus 1 plus 2 plus 1, which is going to be 1/3. Pi 2 is 1 over 2 plus 1 plus 2 plus 1 is 1/6, and then similarly pi 3 is 1/3, and pi 4 is 1/6. So in this case, we actually can easily figure out the stationary probabilities that we'll get if we run it long enough. But for now, let's just assume we don't know that. Is there a question?
Really simple question. Could you just remind me what pi I is?
So pi I is the stationary probability of being in state I. So it's basically, if you run the model an infinitely long time, what fraction of the states you see will be state 1. And any other questions? Okay, so the conditions of the canonical path method apply here. And what we would then need to do, if we want to apply the canonical path method, is come up with the canonical path set for our graph. Now, as I mentioned, we get to pick what this is. We could pick As long as we have something we pick, some path for any pair of nodes, it's okay. But I'm just going to declare J, I'm going to declare that the canonical path is clockwise for I less than J, counterclockwise for I greater than J. So in other words, the canonical path from Q1 to Q2 is just going Q1, Q2. Canonical path from Q1 to Q3 is Q1, Q2, Q3, and likewise Q1, Q2, Q3, Q4. And then the canonical path from, let's say, 3 to 1 is Q3, Q2, Q1, and so forth. So that gives us a canonical path set. And we would then want to use that to look at the edge loading of the different edges in the graph. And that's not necessarily a trivial thing to compute, so I'll walk through a couple of examples, and then we can go through more quickly some of the other ones. So there are 4 edges effectively in this graph. We consider the 2 different directions on each edge to be equivalent. So you have to count the canonical paths twice, but we only need to compute the edge loading twice because it's the same whichever direction you go. All right, so we've got, let's say, the edge loading from 1 to 2. So which canonical paths would use the edge loading, or the edge from Q1 to Q2? Well, basically what we'll have Q1 to Q2 uses it, Q1 to Q3 uses it, Q1 to Q4 uses it, and also Q4 to Q1, Q3 to Q1, and Q2 to Q1. So we've got 6 edges that use that. Now if we want to know what the edge loading is, what we're doing is taking 1 over the capacity. So the capacity would be pi1, p12, or equivalently pi2, p21. We figured out in this case what pi1 was, that's 1/3, and p12 we know is 1/8. So the capacity will be 1/24. And then what we would need to do is sum over all of these terms of the form pi I prime, pi j prime, times the length of the path from pi I to pi j, or from I prime to j prime. So in other words, we know that this edge from 1 to 2 uses the canonical path from 1 to 2. So we're going to get a term that has the form pi1, pi2 times the length of the path from 1 to 2. And the length of the path from 1 to 2 is just 1. That's one edge on the path from 1 to 2. So pi1 we had figured out was 1/3, pi2 was 1/6. So we could figure out that term is going to come out to 1/18. We'll also have a contribution from the canonical path from state 1 to state 3. Can anyone tell me what that would look like? Well, just pi1, pi3. We only need the endpoints for this part of the proof. And then times the length of the path. And pi1 we know is 1/3, pi3 is 1/3, the length is 2. So that's going to be a term of 2/9. And we could say the same thing for pi1, pi4, and then the length of the path from 1 to 4, and that's going to be 1/3 times 1/6 times 3. We also have to take the paths that use that edge in the opposite direction. So we're going to get a pi2, pi1 times the length of the path from 2 to 1, plus a pi3, pi1 times the length of the path from 3 to 1, plus a pi4, pi1 times the length of the path from 4 to 1. And if we go through the math, we could figure out what all of these are. I'm not going to bother writing down all of the individual steps. But basically what this is going to come out to is 1 over 24 times the sum, which in the end is going to come out to 16 over 18 if we work through all of this. And when we work through the math, eventually what we will get is that this is equal to 64 over 3. So that would be the edge loading of that one particular edge. Does everybody follow this? Okay, so we need to know the max edge loading, so we have to consider the other edges as well. There is some edge loading for the edge from 2 to 3. We have to figure out which paths use that one. So this will have 1 over the capacity, and it actually ends up, because of the symmetries in the graph, all of the capacities are 1/24th. So pi I, Pij is always 1/24th in this graph. And then we have to add up contributions from the canonical paths that use the edge from 2 to 3. We get one contribution from the path from 1 to 3, so that passes 1, 2, 3, and that's going to have a length of 2, gamma 1, 3. We get another contribution from 1 to 4 times the length of that path, which is 3. We get another contribution from 2 to 3 times the length of that path, which is 1, and another contribution from 2 to 4 times the length of that path, which is 2. So this will give us a set of contributions for the clockwise paths, and then we'll have a symmetric set of contributions for the counterclockwise paths. So we're going to have a pi 3 to pi 1 times pi gamma 3, 1, plus a pi 4, pi 1, gamma 4, 1, plus a pi 3, pi 2, gamma 3, 2, plus a pi 4, pi 2, gamma 4, 2. And again, I'm not going to bother writing down what each of these evaluates to. We should all be able to figure that out. But if we plug in the numbers in the end, do all the math, this one should come out to 24. So this one is 21 1/3. This one is 24. So this one is now the largest we've seen. We could keep going here, so we would have to figure out pi from 3 to 4. This one, I'm not going to work through all the math of it, but it comes out to 40/3, so that is smaller than 24. And then the last one we would need would be the 4, 1 edge. Then you would figure out what the edge loading of that one is. But which canonical paths use the edge from 4 to 1? Yeah, none of them do, so this is 0. There are no canonical paths use that edge. So we can then conclude that the maximum edge loading for this graph is 24. So, is everyone with me so far?
Can you explain how it got 0 for this?
Yeah, so we get the edge loading. The edge loading is going to be 1 over the capacity, so that's 1 over 1/24th, times this sum over all of the canonical paths that use that edge. And the way I've defined the canonical paths, so they either use these 3 edges in the clockwise direction or the same 3 edges in the counterclockwise. So there's no path that actually uses this edge. So you end up with a 0 in that sum. Any other questions? Okay, so that pretty much gives us what we need to finish our proof of mixing time bound for this model. And I'll leave this up here for a moment because we'll use that later. But basically what we've ended up showing is that maximum edge loading, rho of gamma, is equal to 24. And that means that according to our theorem, mixing time, tau sub q of epsilon, is going to be less than or equal to 24 times the log of pi I inverse. So pi I is going to be the stationary probability of our starting state, and we can actually put a bound on this. The stationary probability is either 1/3 or 1/6, depending on where we start. So we can say that this is never going to be more than 6, so we get a log 6 term, and then a log epsilon inverse term. And that then would give us a bound on the mixing time. We know that for whatever epsilon, if we run it at least this many steps, then it will be mixed within an epsilon bound. Yeah?
Is the inverse on the epsilon or on the log?
Oh, it's on the epsilon.
It's also like a minus sign in the log, because if you move the exponent out to the front.
Yeah, it would be equivalent to a minus sign. So epsilon is usually, for this to be meaningful, you want epsilon to be a small number, so the log will be negative. And then, when you take the minus sign, you end up with a positive value. Any other questions? Okay, so that's kind of a toy example. And we can then go to a more involved example where we can see how this might apply in a biological context. Let's take an example motivated by the problem of studying genetic drift. So I'm going to imagine that we've got a piece of DNA, and let's just say that maybe at one point in time it consists of all A bases, and we'll assume that over successive generations this piece of DNA is mutating. And we might describe that process of mutation by a Markov model where we'll say there's some self-transition probability and maybe some equal probability of having any individual base mutate. So in one generation, we'll just make the simplifying assumption mutation is rare enough. It happens in one base per generation. And maybe on a particular generation, this might mutate so that one of the A's flips to a T, or one of the A's flips to a G, or whatever. And just to keep the math a little simpler, I will assume that the self-transition probability is 1/2. We probably really want that to be much closer to 1, but let's say 1/2. And then that would guarantee, if we're assuming equal probabilities of all other mutations, that if we have a total of n bases here, then all of the others have to be probability 1/6n. So there is a 1/2 probability nothing mutates, and then there are 3n other possible mutations if something does mutate, so 1/6n. And that we would assume would be bidirectional. So if we're in this state, the probability is 1/6n. We go to this state, 1/2 we stay where we are, and so forth. So does that make sense to everyone?
So each DNA strand is one state?
Yeah, we're assuming each DNA strand is one state here. Okay. So what we're going to be interested in here is the mixing time of the Markov model that describes this process. Now, I will say that usually when you use these techniques, what you're trying to do is estimate the stationary probability. But this is an example where maybe what we're interested in is not running this model to find the stationary probabilities, because they're actually pretty trivial to figure out here. We're interested in really how quickly it approaches that. So that might be something we would care about if we were trying to study sequence homology, and maybe we want to know how many generations you can run your model before you lose the ability to detect sequence homology. So something you might be interested in phylogenetics if you're trying to figure out the limits of detection of distantly related genes. So let's just assume that that's what we're trying to do here. We're trying to take this model and we're trying to figure out from the model what is the mixing time, or at least put a bound on the mixing time. Now I said that it's trivial to figure out the stationary probabilities in this model. Can anyone tell me why that is? What are the stationary probabilities?
Is each state equally likely?
Yeah. So we could prove that this model exhibits detailed balance because all of the non-self-transition probabilities have the same value. So any cycle we take, let's say we have a cycle of length k, the total probability of the cycle would be 1/6n to the k in either direction. So we know this exhibits detailed balance. And once you know the model exhibits detailed balance, if you have the same probability in each transition direction, that's telling you pi ji, or pji divided by pij is 1, so pi I divided by pi j also has to be 1. And basically you just follow that chain of inference and you end up concluding every state has the same pi. And in particular, we would be guaranteed that since there are n bases, there have to be 4 to the n possible strings, so pi I is always 1/4 to the n. Okay, so in this case we know that, and that's giving us one of the things we need to verify that the canonical path method applies here. We've shown that the model exhibits detailed balance. So what else do we need to do? What else? What are the other assumptions we need to verify? Yeah. So is this model ergodic? Yeah, if you want to get from any one state to any other, you just flip one base at a time, you'll get to the other state. And the other thing is that it has self-transition probabilities of at least 1/2. And again, I've designed the model, so that's true by design. So we can then proceed with applying the canonical path method. Now, in this case, it's not so obvious what the canonical paths would be. If we're trying to get from any one state to any other states, let's say ACC-AG to GC-AAC, there are lots of different paths we could choose here, and it's not obvious why any one path would be any better than any other. We want to design the paths, though, so that not too many canonical paths are using any one edge. And it ends up for this model, a simple way of doing that is the following. We just say that the path to get from any one state to any other state is the path you get by flipping the bases in order. So in other words, we would go from here to GCC-AG, and then from there to GC-AAG, and then from there to GC-AAC. So in other words, flip the first base that needs flipping, then flip the second base that needs flipping, and so on. So that would give us a canonical path, and we can just say that for any pair of sequences we're interested in, that we would follow that procedure to get our canonical path. And what we then want to do is to figure out, for this model, what is the maximum edge loading in the graph. So we want to say, for any rho sub ij, what is the maximum edge loading? Now in this case, because of the symmetry of the model, it actually doesn't matter which edge ij we pick. They're all going to have the same edge loading. So here we only have to figure it out for one particular edge, or one arbitrary edge. And the first thing we're going to want to do is find this capacity Qij. So that we know is ii Pij. What should that be equal to? We figured out pi I, so pi I is 1 over 4 to the n, and we were given Pij, so that's 1 over 6n, so Qij is 1 over 4 to the n times 6n, 1 over Qij is 4 to the n times 6n. All right, so then the next thing we're going to need to do is to figure out what is the set of canonical paths that use this particular edge ij. And for that one, it is a little complicated for this model. So we'll want to consider maybe a specific example of what this edge might look like, and then look at the canonical paths that take it. So let's say we've got an edge that has the following form. It starts with k minus 1 a bases, then has another base, then has n minus k a bases. And I'm writing it this way because we're going to assume that this is the edge that transitions to k minus 1 a bases, followed by a t, followed by n minus k a bases. So the kth base changes from a to t, and that's the edge we're looking at. Doesn't matter which one we pick, it's just an arbitrary edge we can use. And what we want to ask is, which canonical paths use this edge? Well, if we want to figure that out, one of the first things we can observe is that since our canonical paths were defined to change bases in order, if we're flipping the kth base, we must assume that the previous k minus 1 have already been flipped in every canonical path that uses this. So the only canonical paths that use this have to be ones that end with something that has the prefix of k minus 1a's. We can likewise say that we haven't yet flipped these bases. Since we're flipping the kth, we haven't flipped anything after the kth. So it has to correspond to canonical paths whose starting point has n minus k's as its suffix. And of course, it can't use this edge unless it's making this particular flip, an a to t in the kth base. And then the rest is arbitrary. So we can say, put a wildcard character n here, and a wildcard character n here. Any path of this form, transitioning from something of this form to something of this form, is going to use this edge. Does that make sense to everyone? Okay, so that pretty much gives us what we need to evaluate the edge loading. So we can say the edge loading is going to be 1 over qij times the sum over, say, I prime by j prime, gamma I prime j prime, where, and a lot of this we can simplify. So this we had already seen is 1 over 4 to the n times 1 over 6 to the n. So that gives us a 4 to the n, or 6n term. We know within this sum here, this is going to be 1 over 4 to the n, and this is going to be 1 over 4 to the n. So we can pull those out of the sum. And then we're just left with this sum over gamma I prime j prime. We can simplify a bit, so we can cancel one of those out. And then we've got this thing, which is kind of the hard part to figure out. Okay, but what we want to do is figure out how many paths of this form. And we can do that with a little combinatorics here. We know how many wildcards we have here. So we have k minus 1 arbitrary bases here. We have n minus k arbitrary bases here. So that means in total we have k minus 1 plus n minus k, which is n minus 1 arbitrary bases. And for any particular length of path, then, we can say that we would get a path of length I by choosing the I bases we want to flip among those n minus 1 that we're allowed to flip, and then summing over the possible ways we can flip those. So in other words, what we're saying is the sum over gamma ij is going to be given by the number of paths of length 1. So we're going to get n minus 1 bases we're allowed to flip, and paths of length 1 will be the things we get by not flipping any of those. So by assuming this particular edge is the only edge we flip, so we get n minus 1 choose 0. There's one way to make that change, and then we are going to get a path length of 1 from that. We're also going to have paths of length 2. There will be n minus 1 choose 2 ways to pick the bases that flip in those paths. Excuse me, n minus 1 choose 1. So one of the bases is given to us at a to t flip. We get to pick one more to get a length 2 path. Put in that product of length 2. And then for that one base we flipped, we have 3 possible choices we can make for how we flip that. So that one base we pick could have been one of these A's turning into, or excuse me, could have been one of these bases here turning into an A, or it could have been an A here turning into something arbitrary. In either case, we would have 3 possible choices. Likewise, we can say that there are some length 3 paths. There are n minus 1 choose 2 ways to pick the bases that flip there, 3 squared ways to pick the things they flip into, and then that path has length 3. And in general, we can just keep following this pattern. And what we're going to end up with is that the total edge loading of the model is going to be given by 1 over the capacity, which is 6n over, or excuse me, 1 over the capacity times pi I pi j, which is 6n over 4 to the n, times the sum, which is going to be, if I abbreviate here, sum I equals 0 to n minus 1 of this leading term, which is going to be I plus 1, times the, or excuse me, I plus 1 is the path length, the number of ways of flipping the bases, which is going to be 3 to the I, and the number of ways of picking the bases that flip, which is going to be n minus 1 choose I. So this then is a statement for the edge loading of the graph. Did everyone follow that? Right, so if we want to apply the canonical path method, what we're going to want to do then is figure out what this is equal to. And this is a pretty difficult expression to work with. And that brings about one important point about the canonical path method, as well as the other method we'll be seeing. These aren't absolute proofs of mixing time, they're bounds on mixing time. And because we're using a bound that depends on the value of rho here, it's fine to come up with something that is larger than rho here. It's fine to put in an upper bound of rho, and that will just give us a less tight upper bound on the mixing time. So in other words, we can say that if this is what rho is exactly equal to, then we can say that rho is less than or equal to, let's say, 6n over 4 to the n times a bound on this thing. We can bound this by saying that this can't be more than n, so we'll just pull an n out of here and say that's sum I equals 0 to n minus 1, 3 to the I, n minus 1, choose I. So this is giving us something that will lead to a slightly worse bound than we might get if we could evaluate this exactly, but should be about asymptotically the right order. So we're taking something that can't be bigger than n, and we're just putting an n there in place of it so we can pull it out of the sum. We could do a bound on this thing, but a term like this, it's hard to get a non-trivial bound. But this one, it ends up as kind of a nice trick from combinatorics you can use to solve this. And that is to recognize that this is actually a special case of the binomial theorem. So in particular, if you have anything of the form I equals 0 to m, a to the I, b to the m minus I, m choose I, this is a statement of the binomial theorem for a plus b to the m. And for the right values of a, b, and m, this is this thing. In particular, we can see that a is 3, m is n minus 1, and what is b? 1. Yeah, b is 1. So we can plug in for this that what we get is rho less than or equal to 6n squared, combining those, over 4 to the n, and then this is just 1 plus 3 to the n minus 1, which is 4 to the n minus 1. So that kind of mostly cancels out this thing, and what we're going to end up with is 6n squared over 4, or 3/2 n squared. So did everyone follow that? Okay, and that pretty much brings us to where we need to be to get a mixing time proof. This tells us that tau sub q of epsilon is going to be less than or equal to 3/2 n squared, so that's rho, times the log of pi I inverse. So pi I is always 1 over 4 to the n, so pi I inverse is 4 to the n plus log of epsilon inverse. And log of 4 to the n is just going to be something order of n. So the log of 4 to the n is n times the log of 4. So generally what we would do is abbreviate this and say this is order n cubed plus n squared log epsilon inverse. And that's usually what we would care about for a model like this, is simply the order. So this is basically saying the dominant term is this n cubed. The mixing time of this process is going to be bounded by something that is on the order of cubic with the length of the sequence. That's giving us some notion of, in the outer limit, of how many steps of evolution or how many generations are we going to be able to detect homology of a sequence. So if the sequence has length n, then you can detect it in about cubic time at the most in the number of bases. And that tells us at least something that makes intuitive sense. The more bases we look at, the weaker the homology we'll be able to detect, so the longer the number of generations we can detect homology. So does that make sense to everyone? Now remember that this is an upper bound. It's possible that it will mix in less time than this. And in this particular case, it's not really a tight upper bound. You can actually get better bounds on this particular model, but it gives us an upper bound for this kind of problem. And so, any last questions about the canonical path method? Okay, then I will introduce another method for this kind of thing, which is called the conductance method. And the conductance method gives us an alternative that may be easier to design for some kinds of models and may give a better or worse bound than the canonical path method. So in the canonical path method, the quality of our bound depends on the paths we choose. So there is a kind of design decision there. In the conductance method, you don't get to choose anything, and it's kind of specified for you how you do everything in the conductance methods. That can be good and bad, but the actual bound you get out at the end could be better or worse. And the intuition behind the conductance method is as follows. Let's say we've got some complicated graph. What the conductance method is considering is if we look at subsets of the graph, and let's take a subset we call S, so a subset of the states. What the conductance method is saying is if there is no subset of the graph that is hard to get out of, that we have a high probability of being in. So basically, if there's nowhere you easily get stuck when you're sampling from this model, then the model has a good mixing time. And that's formalized through a quantity called the conductance, which we'll call phi of S, which is defined as follows. It's going to be the sum over Qi in S, Qj not in S, of capital Q sub ij, which is the capacity term we saw before, these Pij's, divided by what we're going to call capital pi of S, which is simply the sum over Qi in S of pi I. So just the stationary probability of being in state S. And what this is saying is the numerator here is kind of your ability to get in or out of this state S. It's the sum of these capacities. The denominator is the amount of time on average you spend in state S. So if the numerator is big, then that means it's easy to get in or out of these states. If the denominator is small, then that means you don't spend a lot of time in them. And a model where every subset S has a good conductance, so that is a large conductance, is a model where it's hard to get stuck in any subpart of the graph. And so what we can do is use, we'll call this capital phi here, is simply the minimum over all of these phi s's. We have to add the additional condition S subset of Q, such that 0 less than or equal to phi of S less than or equal to 1/2. So in other words, we're considering subsets that occupy no more than 1/2 of the Markov chain, so no more than 1/2 of the stationary probability. And if we can show that this minimum phi is relatively large, then we can show that our model has a good mixing time. Does that make sense to everyone? Yeah?
Yeah, like so is there a reasonable cutoff for this, or of this conductance?
Well, there isn't exactly a hard cutoff. You would usually be trying to prove something like the rapid mixing that I showed before, where in terms of some parameter n, it's polynomial in n, something like that. So to explain that, what we would use is that there's a theorem analogous to the one we saw for the conductance method that says under the same conditions, a given finite inversible ergodic Markov chain with PII greater than or equal to 1/2 and conductance phi, then tau sub q of epsilon, or tau sub qi of epsilon, is less than or equal to 2 phi to the minus 2 log of pi inverse plus log of epsilon inverse. So in other words, if you can show the conductance is polynomial or really 1 over a polynomial in the size of model you're looking at, then you can show that you have a rapidly mixing model. So the bound we get varies inversely with the square of the conductance. Is there any questions about that? Yeah.
Why is the time defined for a specific QI?
It doesn't need to be. This is coming from one of the references I use. If you look in the textbook, there's a reference to some of the, well, a book chapter based on the seminal work in this area. They defined it this way. You could always define it to be maximized overall possible QI, and I think that would be fine to do. Any other questions? Okay, so let's see then in a toy version how this would work. And we can use the same graph we had from the beginning here, these 4 states. And we could try to figure out what are the conductances for different subsets of this graph. So we could take, for example, S equals, let's say, the states Q1 and Q2. So in this graph, that would be taking these 2 states, defining that to be S. And we would then want to figure out the ratio of the capacity of the edges in and out of that subset to the stationary probability of being in that subset. So the edges in and out of the subset are the edge from 1 to 4 and the edge from 2 to 3. So we've got 2 of these. And as we saw before, each of those is going to have a capacity of, that would be 4 plus 2, 2, 3. Each of those is going to be 1 over 24. So the numerator here will be 1/12. And the denominator we're going to get by taking stationary probability of state 1 plus stationary probability of state 2. And if we remember from before, that's 1/3, 1/6. So those add to 1/2. And then if we divide through, we're going to get 1/6. So the conductance for this particular definition of S is 1/6. Now, just as in the canonical path method, we need to consider every edge and find the maximum edge loading. In this case, we need to consider every subset S that satisfies this condition to get the minimum conductance. So we can take another example. We can look at Q2, Q4. So Q2, Q4 is this state and this one. And you might note those aren't contiguous. There's no rule that these have to be contiguous in the graph. So we can pick those. We are then going to get, in this case, basically every edge in the graph. So Q2 to Q1, Q2 to Q3, Q4 to Q1, Q4 to Q3. So we have to consider 4 possible Qs. So Q1, 2 plus Q2, 3 plus Q1, 4 plus Q3, 4. Those are all 1/24, so we've got 4 over 24, which is 1 over 6. And we've got pi 2 plus pi 4. Those are both 1/6, so we get 1/3 in the denominator. So in other words, we're going to get 1/6 divided by 1/3, which is 1/2. And this conductance is larger than this one, so this is the one we care about so far. We can also consider single states. Let's say Q1. So what would be the conductance for S equals Q1? Well, we need to consider that there are 2 edges between S and not S. So we've got 2 over 24 for the numerator here. Our denominator is just going to be pi of state 1, which is 1/3. So we've got 1/12 divided by 1/3, which is 1/4. And we could likewise consider Q2. In that case, we're also going to get 2 over 24 for capacity, 1/6 for the stationary probability. So we're going to get 1/2 here. Q3 would be the same as Q1. Q4 would be the same as Q2. We don't need to consider Q1 and Q3. Why is that? Why don't we need to worry about S being Q1 and Q3?
Because the stationary state probabilities are not known and not.
Yeah, that would have a stationary probability of 2/3, so that fails this condition here. So basically we've considered every case for a minimum conductance. And that gives us everything we need to set our mixing time bound for this model by this particular method. So in particular, we can say tau sub q of epsilon is going to be less than or equal to 2 times 1/6 to the -2 times log of pi inverse plus log of epsilon inverse. Pi inverse we know is bounded by 6. 1/6 to the -2 is going to be 36. We get 72 times log of something that's opposed to 6 plus log of epsilon inverse. And that gives us a bound for this particular model by the conductance method. We know this many steps is adequate to mix the model. In this case, this has actually given us a worse bound than the canonical path method gave for this problem. That's not guaranteed to be true, so in some cases this works better, some cases canonical path works better. All right, so any questions about how we use the conductance method? Okay, well, let's take then a less trivial example of a conductance method group. In this case, what I'm going to look at is another kind of problem we might care about in biological modeling. In this case, something that comes up in biophysical contexts, and that is known as a bounded random walk. So a random walk is a kind of Markov model we often use to model diffusion processes. So in a two-dimensional case, a random walk might be something we would represent by creating a grid graph where the states are points on the grid and tracking something that jumps between adjacent grid points. That's a model of two-dimensional diffusion. In this case, I'll make it a little easier for the proofs by saying that we'll look at a one-dimensional bounded random walk. And that's going to look like the following. To make things a little easier, I'll skip a step that's in the example in the text, and I'll just say that we're going to assert that each of these internal states has a self-transition probability of 1/2. And then we'll have a couple of end states, that's what makes it bounded, that have self-transition probabilities of 3/4. And then we're going to assume that between any adjacent states in this random walk, we're going to have bidirectional edges with probability 1/4 in each direction. And then we can imagine that the state of this model is describing movement of a particle in a one-dimensional channel and models the diffusion of that particle. And what we might be interested in is if we put a particle in at one end of the model, how long does it have to sit there before we can assume it's well mixed? So that is, that it's diffused. It's a way of getting a bound on, as a function of, let's say, length of a channel, how quickly do things diffuse. Right, so that's our model here. And what we would want to say is, if we assume that we have n states in this model, can we put a bound on the mixing time of the overall model? And so just as with the canonical path method, we would want to verify that this is ergodic. So in this case, it's pretty clearly ergodic. You can just jump from any one, by a series of successive states from any one to any other. We've defined it so PII is greater than or equal to 1/2. And does this model exhibit detailed balance? Yes, so in this case, the underlying graph, if we collapse bidirectional edges, just treat them as one edge, the underlying graph is a straight line. In fact, anything where the underlying graph is a tree of any form trivially satisfies the Kolmogorov criterion. So in this case, this satisfies the Kolmogorov criterion. And because all of the pairs of edges have the same probability going one way as the other, that also guarantees that our stationary probabilities are all the same. So we know that every pi I is going to be 1 over n. Okay, so this satisfies the conditions of our method. What we would then want to do is figure out, over all of the possible subsets S, what is the sum of Q over pi. In the text, I go through this in somewhat more detail than I'm going to go through it here. I'll just give you kind of a quick, more hand-wavy proof of what this could possibly be. So in particular, let's say that we are looking at our model and we're considering some subset of, let's say, M states. So we're defining S to be some mix of M states. And for the moment, let's say that when we're looking at this random walk model, let's say it's just some arbitrary mix, maybe a few from here, a few from here, a few from here, that adds up to M states. What then is pi of S?
M over.
Yeah, so pi is M over n. It doesn't matter how we picked where the states are because they all have the same stationary probability. It does matter what Q is, what the Q for this is. So in particular, the sum of Qij. But what we want to do is find the smallest possible conductance. So we want to find the way of positioning our M states to minimize Q. No matter how we position them, we get the same pi. So we position them to minimize Q. And Q is going to be a constant for each edge here. So every edge is going to have the stationary probability times the edge value. That's going to be 1 over n times 1/4. So we're going to have that every Qij is 1 over 4n. And so what we want to do is figure out how to position our M states to have as few edges between S and not S as possible. And it should be pretty clear that the way to do that is just pick the first M states. Then we've only got one edge between S and not S, and that's going to minimize the numerator. In particular, that's going to give us phi of S equals the Q contributed by that one edge, 1 over 4n, divided by the pi for those M states, that's M over n, which is going to come out to 1 over 4m as over phi. Now we want to find the smallest possible conductance over the entire graph, so we want to figure out what value of m makes this as small as possible. So what value of m should we use?
N minus 1.
Sort of. We want, so we want m to be big. The bigger m is, the smaller the conductance will be. But we have the same condition, pi of s can't be more than 1/2. So basically we want to use half the nodes. So we want m equals n over 2, and that's going to give us that this is 1 over 4, n over 2, which is going to be 1 over 2n. So that then is telling us that the minimum phi, so this thing we call capital phi, is 1 over 2n, and that basically is everything we need to get our conductance method bound. So we've got that phi is 1 over 2n. We plug in, then that's telling us that tau sub qi of epsilon is going to be less than or equal to 2 times 1 over 2n to the minus 2 times log of, well, pi I inverse. Pi we know is always 1 over n, so this is just going to be n. 1 over n inverse is n, plus log of epsilon inverse. And then if we work through the math here a bit, what we're going to end up with is that this is going to be 4n squared, so we're going to get 8n squared times log n plus log epsilon inverse. So that then is going to tell us that this will mix in a time that is bounded by something of the order of n squared log n. In this case, again, it's not entirely a tight bound, so you can actually prove by other methods that this order n squared is the time you need to diffuse in something of length n, but basically this gives us an upper bound, at least a general idea, on an upper limit of how long you would need to run this model to mix it accurately. All right, so any questions about that? Okay, so we've got a few minutes here, so I want to kind of very quickly tell you about one other method that's not covered in the text, but is worth knowing about because it's become really the most popular method people use for these things. And it also tends to give better bounds than these other methods we've covered. And that's something called the coupling method. And coupling is a little tricky to describe, but once you see an example, I think it's relatively easy to understand what it is. So a coupling is something we create from a Markov chain by taking two copies of the Markov chain. So it's really, if we have a Markov chain with state set Q, then the coupling has a state set Q cross Q, so it has a pair of these Markov chains. And they're defined in such a way that if we have our original Markov chain and we create these paired Markov chains, so each state is some tuple xy, then if we look at the model for x and just ignore what's happening to y, this is a copy of our original Markov chain. And if we look at the model for y and ignore what's happening to x, this is also a copy of the original Markov chain. It follows exactly the same transition probabilities. But it has to be designed in a way that even though each of these is a copy of the original Markov chain, they're not independent copies. So you have to design the rules for the pair of them behaving so that each behaves like the original chain, but that they are coupled in a meaningful way. And we'll see in a moment what that means. So in particular, what we're going to try to do with a coupling proof is show that, in a sense, you can set up the rules so that in a relatively short number of steps, no matter where we start these two different chains, they will turn into the same state. So they'll eventually start doing exactly the same thing. You have to design them so that they will do this. And you can kind of think of it that what you're trying to do is show that if you can get quickly from any starting state to any two other states, then you can also think about sort of reversing time and saying that then in reverse time you should be able to get from any two arbitrary states back to some common state. And I know that's a really confusing way of explaining this, but I think it'll be clearer once I show a concrete example. But what we're going to try to do with these is to define a distance, what we'll call d of xy, between the two chains. And we're going to try to find a quantity which we'll call delta sub d, which is the minimum of the expected value of the distance between the chains at state I minus 1 minus the distance at state I. We're going to want this delta to be big. So on average, the chains get more similar on successive steps, and we want to show that on average they get more similar by as much of an amount as we can show. And we also are going to want to define some d max, which is simply the maximum over all possible x and y of dxy. And basically what the proof is going to show is that we can put a bound on our tau to be less than or equal to d max over delta d. So if you can show that on average, on each successive step, they get closer by at least a factor of delta d, and they can't be farther away ever than d max, then basically you don't need more than d max over delta d steps on average to mix them. And that's how the proof is going to work in most of when you use these kinds of models. The hard part of a coupling proof is coming up with the coupling. And I can illustrate how that works by taking one of the models we saw earlier in this class, and that is our sequence evolution model. So let's say we've got our sequence evolution model, we've got our string of bases, we've got self-transitions of 1/2, we've got transitions to any other single base mutation of 1 over 6n. That's going to be our original Markov model, and I'm going to define a coupling made of a pair of versions of this model. And the coupling is going to work as follows. From any given state, so any pair of sequences x and y, we're going to say is first, with probability 1/3, do nothing. So xi minus, or xi, xj is going to be simply, or xi, yi is going to be xi minus 1, yi minus 1. Next states are equal to the previous state. Otherwise, so with probability 2/3, pick a base 1 to n uniformly at random. So with probability 1 over n, pick any of the n bases in the sequences. If xi is equal to yi, then pick uniformly from ACGT. So pick each among these with probability 1/4, and you say, I guess I abused notation a bit here. Here I'm saying the ith base of x. The ith base of x gets this thing, let's call that c, and the ith base of y also gets c. Otherwise, the ith base of x gets AC GT uniformly at random, and the ith base of y independently gets an AC G or T uniformly at random. So in other words, what this is saying is we take whatever state we're in at the current point in time, probability 1/3, you just stay in that state for the next point in time. If you don't do that, then we pick a base uniformly at random. If that base happened to have the same character in x and y, then we pick a new character and put that base into both x and y in that position. And you might notice that this is guaranteeing that once a base agrees between x and y, it has to agree in every subsequent step, and that's important. If the base that we pick doesn't agree, so xi and yi are not the same, then we pick uniformly at random for x and y. So if they don't agree, they may still not agree on the subsequent step, although there's a 1 in 4 chance they will end up picking the same value, and then they agree, and that base will agree for all subsequent steps of the coupling. All right, so that defines our coupling, and what we would want to verify is that this coupling is for x is our original Markov model, and for y is also our original Markov model. So if we take x, then we can ask, what is the self-transition probability for just x ignoring y? Well, there's a 1/3 probability we do nothing in the first step, so that's one way we can get a self-transition in x. And then there's a 2/3 probability we don't use that condition, but if we don't use that condition, then there's still a 1/4 probability in either this condition or this one, we happen to pick the base that was already in position I for x. So there's a 1/3 plus 2/3 times 1/4 probability that we don't change x. And if we add that up, that's going to come out to 1/2, which is what we want. So the self-transition probability for x is 1/2, which is what we had in our original Markov model. And the probability we change x, so x in step I plus 1 is not equal to x in step I, is then going to be also 1/2. And it's going to be equally likely to be any other change. So if we do change it, whether we're in this condition or this one, we're equally likely to change any particular base. So the probability of any particular change is going to be 1 over 6n. There are 3n ways we could change x. They're all equally likely. And that also is what we had in our original model. So this is verifying that x in the original model, if we ignore y, or x in the coupling, if we ignore y, is exactly our original Markov chain. And by symmetry, that means y, if we ignore x, is exactly our original Markov chain. But they've been designed in such a way that once two bases become the same in them, they're always the same. They can't change to anything else. And that lets us figure out some of these properties. In particular, we can say that delta D is the expected amount by which they become more similar on each step. They can never become more different on subsequent steps. The same base for xi and yi. And we can say that the probability of that occurring is going to be 2/3 probability that we decide to change something, so we don't pick the do nothing step, and we're in this one. And then the probability we pick a base that wasn't already the same, and that probability is simply going to be the distance between the sequences. And we can define a very obvious distance between the sequences, just how many bases disagree. So if we define that, then the probability we make the sequences more similar is going to be proportional to the distance between them, the number of dissimilar bases divided by the number of similar bases, times the probability we happen to pick the same new value for that base in the two sequences. So in other words, delta D is going to be equal to 1/6n times d of xy. And we want delta D to be as small as possible. We're trying to put a lower bound. If they're not already identical, D has to be at least 1, so that's going to be 1/6n. On each step until they're identical, we have an expected increase in similarity of at least 1/6n. We have D max. Can anyone tell me what D max is? We've defined the distance between the sequences to be the number of bases that disagree. If we have n bases, you can't have more than n disagreeing. And that pretty much gives us everything we need to complete our proof. We need to figure out, to put our bound on tau, that this is going to be less than or equal to d max divided by delta d. So that's n over 1/6n, which is going to be 6n squared, or order n squared. So in this case, we get a better bound than we got with the canonical path method, and although I know some of this is a little confusing, it's actually often a much easier technique to use than the canonical path method. So we get a better bound and a simpler proof. So that's really why people often now prefer this coupling method. It tends to be easier to use once you understand it, and it tends to give better bounds than the other methods. And so I think we're out of time here. Are there any last questions before we break? Okay, then I'll see you all on Thursday.